Orion and Betelgeuse, the dimming of the hunter. Introduction: the hunter's eternal watch. In the vast theater of the night sky, few celestial patterns command attention like the constellation Orion. For thousands of years, humans have looked up and recognized this cosmic hunter, his form outlined by some of the brightest stars visible from Earth. The constellation rises in the east during winter months for northern observers, climbing steadily across the sky until it dominates the celestial dome. Ancient civilizations across continents independently recognized these stellar patterns, weaving them into their mythologies and using them to mark the changing seasons. The constellation's most distinctive feature remains Orion's belt, three brilliant stars aligned in a nearly perfect row. Alnitak, Alnilam, and Mintaka shine with bluish-white light, each a massive supergiant burning tens of thousands of times brighter than our sun. These stellar giants mark the hunter's waist, and from this central landmark the eye can trace the rest of his form. Above the belt, two prominent stars mark Orion's shoulders. On the western shoulder sits Bellatrix, whose name derives from the Latin for female warrior. This blue-white giant shines steadily at magnitude 1.6, maintaining its position as the third brightest star in the constellation. But on the eastern shoulder, something extraordinary captures our attention. Here blazes Betelgeuse, a star so fundamentally different from its neighbors that it stands out even to the casual observer. While most of Orion's bright stars glow with the blue-white fire of young, hot suns, Betelgeuse radiates with a deep orange-red hue. This color difference signals something profound about the star's nature. Betelgeuse belongs to a rare class of stellar giants, the red supergiants, stars that have reached the twilight of their existence and swollen to truly astronomical proportions. The name Betelgeuse comes to us from Arabic astronomy, derived from Yad al-Jawza, meaning the hand of the giant, though over centuries of translation and transcription, it evolved into its current form. English speakers often pronounce it Betelgeuse, a convenient, if somewhat undignified rendering of an ancient name. Yet regardless of how we say it, this star represents one of the most remarkable objects visible to the naked eye. When we observe Betelgeuse on a clear winter night, we witness a star in crisis, a massive sun that has burned through its core hydrogen and entered the final chapters of its stellar life story. The constellation Orion stands as more than just a collection of bright stars. It represents a region of intense stellar activity, a cosmic neighborhood where stars are born, live, and die. The Orion Molecular Cloud Complex, a vast region of gas and dust extending hundreds of light-years across space, encompasses the entire constellation and serves as one of the most productive stellar nurseries in our section of the Milky Way galaxy. Within this cloud, gravity compresses hydrogen and helium into dense cores that ignite through nuclear fusion, creating new stars. The Orion Nebula, visible as a fuzzy patch below the belt, offers a window into this ongoing process of stellar birth. Yet while new stars emerge from the nebula's dusty embrace, older stars like Betelgeuse approach their inevitable end. The cosmic cycle continues, destruction feeding creation, as dying stars return their enriched material to the interstellar medium, providing the raw ingredients for future generations. Betelgeuse stands as a monument to this cycle, a star that once burned with the blue-white intensity of youth and now swells with the cooler, redder light of old age. The star's size defies easy comprehension. If we could somehow transport Betelgeuse to the center of our solar system, replacing our sun, its outer atmosphere would extend past the orbit of Mars, possibly reaching as far as Jupiter. The star measures roughly 764 times the diameter of our Sun, though this number varies because Betelgeuse constantly pulsates, expanding and contracting like a cosmic heartbeat. In volume, Betelgeuse exceeds our Sun by a factor of at least 160 million. Yet despite this enormous size, the star's mass totals only about 16 to 20 times that of our Sun. This means the star's average density approaches nearly nothing, more rarefied than the vacuum inside a laboratory bell jar. We could fit our entire solar system inside Betelgeuse with room to spare. Despite its low density and relatively cool surface temperature of around 3,600 Kelvin, Betelgeuse radiates between 90,000 and 126,000 times more energy than our Sun. This immense luminosity arises from the star's vast surface area. Every square meter of Betelgeuse's photosphere emits less energy than an equivalent area on the Sun, but the star possesses so much surface area that its total energy output dwarfs that of our parent star. Much of this radiation emerges not in visible light, but in infrared wavelengths, heat that our eyes cannot detect, but that infrared telescopes reveal in stunning detail. The distance to Betelgeuse has proven surprisingly difficult to measure with precision. Current estimates place the star approximately 550 to 700 light-years from Earth, meaning the light we see tonight left the star sometime during the late medieval period or early Renaissance. We observe Betelgeuse not as it exists now, but as it appeared centuries ago, a window into the deep past. This temporal disconnect adds an extra layer of mystery to the star's behavior. When Betelgeuse finally explodes as a supernova, an event that could happen anytime in the next 100,000 years, the explosion will already be ancient history by the time the light reaches Earth. For observers through the ages, Betelgeuse has exhibited notable variability in brightness. The star pulsates on a roughly 420-day cycle, expanding and contracting as it burns helium in its core and hydrogen in a shell surrounding that core. During these pulsations, the star's brightness can vary by more than half a magnitude, enough to be noticeable to careful observers. Ancient astronomers noted these changes, though they lacked the tools to understand their cause. Some historical records suggest that Betelgeuse once appeared more yellow or white than its current orange-red color, though these observations remain subject to interpretation. Yet nothing in Betelgeuse's long history of observation prepared astronomers for what began unfolding in late 2019. The star embarked on an unprecedented dimming episode, dropping to the faintest level observed in nearly 2 centuries of careful record-keeping. This dramatic change sparked intense interest across the astronomical community and captured public imagination worldwide. People wondered whether they were witnessing the precursor to a supernova explosion, a stellar death that would briefly outshine all other stars in the night sky and remain visible even during daylight. The timing, the scale, and the unexpected nature of the dimming all contributed to a mystery that demanded investigation. Investigation, the Great Dimming and its secrets. The story of Betelgeuse's Great Dimming begins in October 2019, when astronomers monitoring the star noticed something unusual. The star, which typically varies in brightness according to its established pulsation cycle, started dimming more dramatically than expected. Month by month, the light output decreased, until by mid-February 2020, Betelgeuse had lost more than 2/3 of its normal brilliance. The star that had held the position of second brightest in Orion now appeared dimmer than several of its constellation mates. For the first time in living memory, casual observers could notice a significant change in one of the sky's most prominent stars without needing telescopes or careful measurements. The astronomical community mobilized rapidly. Telescopes around the world and in orbit turned their attention to Betelgeuse, attempting to capture data that might explain this extraordinary behavior. Professional astronomers worked alongside amateur observers, creating a comprehensive monitoring campaign. Every wavelength of light became a potential clue. Optical telescopes tracked the visible dimming, infrared observations probed the star's thermal output, and radio telescopes examined the behavior of molecules in the star's extended atmosphere. Initial theories proliferated as scientists scrambled to explain what they were seeing. One early hypothesis suggested that an enormous dark spot had formed on the star's surface, similar to but far larger than the sunspots that appear on our Sun. Such a spot would represent a cooler region on the stellar surface, reducing the total light output. The idea had precedent, as interferometric observations had previously revealed bright and dark patches on Betelgeuse's photosphere, evidence of the massive convection cells that roil the star's outer layers. Another possibility considered was that Betelgeuse had ejected a massive amount of dust into space, and this dust cloud now lay between the star and Earth, blocking a portion of its light. Red supergiant stars like Betelgeuse constantly lose mass through powerful stellar winds, shedding material into space at rates far exceeding anything our Sun produces. Perhaps some unusual event had triggered a particularly intense outburst, creating enough dust to obscure the star. The most dramatic possibility captured public attention above all others. Perhaps Betelgeuse was preparing to explode. Massive stars like Betelgeuse end their lives in catastrophic supernova explosions, and while astronomers expected Betelgeuse to remain stable for at least several more tens of thousands of years, no one could completely rule out the possibility that the star's time had come. The idea of witnessing a supernova at such close range excited astronomers and the public alike. A supernova at Betelgeuse's distance would become the brightest stellar explosion observed since 1604, easily visible during daylight and potentially brighter than the full moon. As observations accumulated, a clearer picture began to emerge. The Hubble Space Telescope, with its ability to observe in ultraviolet wavelengths, proved crucial to understanding what had occurred. Ultraviolet observations allowed astronomers to probe the hot layers of Betelgeuse's atmosphere above the visible photosphere, regions where temperatures exceed 20,000 degrees Fahrenheit. These observations revealed evidence of massive convection cells, enormous bubbles of hot gas rising from deep within the star, similar to but vastly larger than the granules visible on the Sun's surface. In September through November 2019, just before the visible dimming began, Hubble detected material moving at approximately 200,000 miles per hour through the star's outer atmosphere. This represented something extraordinary. Normal stellar wind velocities for red supergiants measure in the tens of miles per second, not hundreds of thousands. Something had violently ejected a massive amount of material from the star's surface. Astronomers dubbed this event a surface mass ejection, or SME, analogous to but far more powerful than the coronal mass ejections that our Sun occasionally produces. The mechanism behind this ejection involved the complex interplay of forces within Betelgeuse's outer layers. Red supergiants possess enormous convective envelopes, regions where energy transport occurs primarily through the physical motion of hot gas rather than through radiation. Within Betelgeuse, massive convection cells hundreds of millions of miles across carry heat from the deep interior toward the surface. These cells rise, cool, and sink back down in a continuous cycle, creating a roiling, turbulent photosphere. Occasionally, these convection cells can become particularly vigorous. When a large cell reaches the surface, it can create shock waves that propagate through the atmosphere. These shocks can accelerate material to enormous velocities, potentially ejecting it entirely from the star. In early 2019, observations suggest that such an event occurred on Betelgeuse. A powerful convection cell reached the surface, creating shocks that blasted a portion of the photosphere into space. The ejected material, several times the mass of our moon, traveled outward from the star. As this material moved through Betelgeuse's extended atmosphere, it encountered cooler temperatures. Red supergiant atmospheres are complex, layered structures. The visible photosphere represents only one layer. Above it extends a vast envelope of cooler gas, gradually transitioning to the surrounding interstellar medium. As the ejected material passed through this cooler region, the conditions became right for dust formation. Silicon, oxygen, and other elements in the ejected gas began combining to form tiny solid particles, creating what astronomers call dust grains. This dust cloud, containing silicon monoxide and other compounds, formed millions of miles from the star's surface. The cloud measured over 100 million miles across, far larger than the entire inner solar system. As it drifted away from Betelgeuse, this cloud passed directly between the star and Earth, blocking a significant portion of the star's light. The dust acted like a cosmic veil, scattering and absorbing photons before they could reach our telescopes. This explained the dramatic dimming observed from Earth. Imaging observations from the European Southern Observatory's Very Large Telescope provided direct visual evidence for this scenario. The SPHERE instrument on the VLT can create direct images of stellar surfaces, an extraordinary capability considering the vast distances involved. Images taken in January 2019 showed Betelgeuse at its normal brightness, with the expected bright and dark patches indicating convection cells on the surface. Images from December 2019 and January 2020 showed something dramatically different. The star's southern hemisphere appeared much darker than normal, and a distinct asymmetry had developed. The southern region appeared nearly 10 times fainter than usual. Additional evidence came from spectroscopic observations. Spectra taken during the dimming event showed changes in the absorption lines created by various molecules and atoms in the star's atmosphere. Lines from titanium oxide, a prominent feature in red supergiant spectra, showed variations consistent with a temperature decrease in the southern hemisphere. The effective temperature of the affected region appeared to have dropped by at least 170 Kelvin compared to normal conditions. The combination of evidence painted a comprehensive picture. A surface mass ejection had occurred, triggered by vigorous convection within the star. This ejection blasted hot material from the photosphere into the cooler outer atmosphere. As this material cooled, it condensed into dust grains that formed a cloud obscuring the star's southern hemisphere as seen from Earth. The southern surface itself had also cooled, contributing to the dimming through both the obscuring dust and the lower intrinsic brightness of the cooled region. By April 2020, Betelgeuse began recovering its normal brightness. The dust cloud had dispersed or moved out of the line of sight, and the cooled region of the photosphere had warmed back to its typical temperature. The star climbed back to its expected luminosity, though observations suggested that its normal pulsation cycle had been disrupted by the violent events of the previous months. The deep interior of the star had essentially been perturbed, and it would take time for the normal rhythms to re-establish themselves. This interpretation solved the immediate mystery of the Great Dimming, but raised deeper questions about red supergiant behavior. How common are such surface mass ejections? Do all red supergiants experience them, or had something special occurred on Betelgeuse? What role do these ejections play in the overall mass loss process that characterizes the final stages of massive star evolution? Red supergiants shed enormous amounts of mass during their brief lives as cool giants, losing perhaps a solar mass or more over a few 100,000 years. The Great Dimming suggested that this mass loss might not occur as a steady wind, but through episodic, violent ejections. The event also highlighted the dynamic nature of red supergiant atmospheres. Traditional models of stellar structure often treat a star's outer layers as relatively stable and uniform, changing slowly over time as the star evolves. Betelgeuse demonstrated that reality is far more complex. The star's atmosphere seethes with activity, massive convection cells churning the photosphere, shock waves propagating through the outer layers, and dust forming and dissipating in the extended envelope. Red supergiants exist in a constant state of instability, their outer layers barely bound by the star's gravity. The role of convection in creating the surface mass ejection deserves closer examination. Convection occurs when energy transport by radiation becomes inefficient, forcing the star to transport heat through the physical motion of gas. In a red supergiant, the outer layers are cool and opaque, making radiative transport difficult. Instead, hot gas rises from below, cools as it approaches the surface and sinks back down, creating convection cells. The scale of these cells in Betelgeuse dwarfs anything seen on the Sun. Solar granules measure roughly 1,000 kilometers across, about the distance from New York to Chicago. Betelgeuse's convection cells span hundreds of millions of kilometers, larger than the orbit of Earth around the Sun. These enormous cells take months or even years to complete a cycle, rising, cooling, and sinking. When observed through interferometric techniques that can resolve the star's surface, these cells appear as bright and dark patches, the bright regions representing hot rising gas and the dark regions cooler sinking material. Occasionally, a particularly vigorous convection cell can generate shocks powerful enough to exceed the escape velocity from the star. When this happens, material gets blasted into space rather than falling back to the surface. The energy for this comes ultimately from the nuclear fusion occurring in the star's core, but the immediate driver is the buoyancy of the hot convection cell and the momentum it carries upward through the star's outer layers. The formation of dust in the ejected material represents another crucial piece of the puzzle. Dust grains in space typically form when gas cools to the point where atoms can stick together, creating small solid particles. In the immediate vicinity of a star like Betelgeuse, temperatures remain too high for dust formation. The photosphere glows at 3,600 Kelvin, and even the lower atmosphere maintains temperatures of several thousand degrees. But as material moves outward from the star, it expands and cools. By the time ejected material reaches distances of several stellar radii from Betelgeuse's surface, temperatures have dropped to perhaps 1,000 to 1,500 Kelvin, cool enough for dust to condense. Silicon monoxide molecules in the cooling gas serve as condensation nuclei. Silicon and oxygen atoms, products of the nuclear fusion that has occurred in Betelgeuse's core over millions of years, combine to form CO molecules. As temperatures drop further, these molecules can stick together, growing into larger clusters. Other elements contribute to the dust formation process as well. Carbon, nitrogen, iron, and magnesium all participate in creating various dust species. The exact composition of the dust depends on temperature, density, and the relative abundances of different elements in the ejected material. Once formed, dust grains interact strongly with light. Their size, typically a fraction of a micron to a few microns across, matches well with the wavelengths of visible light. This makes them extremely efficient at scattering and absorbing photons. A relatively small mass of dust can therefore block a significant amount of starlight. During the Great Dimming, the dust cloud that formed around Betelgeuse's southern hemisphere blocked light equivalent to about a quarter of the star's surface area, despite the dust itself representing only a tiny fraction of the star's total mass. The chemical analysis of Betelgeuse's atmosphere and the dust in its vicinity reveals the star's history of nuclear fusion. The elements present in the outer layers tell us which fusion processes have occurred and which products have been mixed to the surface. Betelgeuse's spectrum shows enrichment in nitrogen relative to carbon, a signature of CNO cycle hydrogen fusion that has been mixed to the surface through convection. The presence of oxygen, silicon, and other heavy elements reflects the helium fusion currently occurring in the star's core. This brings us to the question of what happens inside Betelgeuse, to the nuclear furnace that powers this enormous star and determines its fate. Understanding Betelgeuse's interior requires understanding the life cycle of massive stars and the nuclear physics that drives their evolution. The nuclear furnace and stellar death. To understand Betelgeuse's present state and future fate, we must journey to its beginning. The star formed roughly 8 to 10 million years ago from a giant molecular cloud, a vast region of gas and dust floating in the interstellar medium. Something, perhaps a shock wave from a nearby supernova or the gravitational influence of a passing star, disturbed this cloud, causing a portion of it to collapse under its own gravity. As the gas compressed, it heated, and a core of increasing density and temperature formed at the center of the collapsing region. When the core temperature reached about 10 million Kelvin, nuclear fusion ignited. Hydrogen nuclei, essentially bare protons, began fusing together to form helium, releasing tremendous amounts of energy in the process. This energy pushed outward against the inward pull of gravity, establishing a balance called hydrostatic equilibrium. A star was born. The young Betelgeuse would have looked nothing like its present appearance. Instead of a cool, red supergiant, the infant star blazed as a hot, blue giant, perhaps an O-type or early B-type star with a surface temperature of 30,000 Kelvin or more. With an initial mass somewhere between 15 and 20 times that of our Sun, Betelgeuse joined the rare class of massive stars. These stellar giants live fast and die young compared to stars like our Sun. While the Sun will fuse hydrogen in its core for roughly 10 billion years, massive stars like Betelgeuse burn through their core hydrogen in just 10 million years or less. The higher core temperature and pressure in massive stars drives fusion reactions at a furious pace, generating enormous amounts of energy but depleting the fuel rapidly. For the first several million years of its life, Betelgeuse remained on what astronomers call the main sequence, the stable phase where stars spend most of their lives fusing hydrogen into helium in their cores. The star maintained a roughly constant size and brightness during this period, though it would have been far larger and brighter than our Sun. The nuclear reactions in the core converted roughly 4.3 million tons of matter into pure energy every second, according to Einstein's famous equation E equals mc2. This energy flowed outward through the star, eventually radiating into space from the photosphere. But nuclear fusion cannot continue indefinitely. The hydrogen fuel in the core, though abundant, is finite. As fusion proceeds, helium ash accumulates in the stellar core. Helium nuclei, being heavier and more compact than hydrogen, settle toward the center under gravity. Gradually, the core transforms from mostly hydrogen to mostly helium, while hydrogen fusion continues in a shell surrounding the helium core. This marks the beginning of the end for a star's main sequence life. When the core becomes predominantly helium, the nuclear reactions that have sustained the star for millions of years sputter and die. Hydrogen fusion requires hydrogen, and with the core depleted of this fuel, energy generation in the core ceases. The star faces a crisis. Without the outward pressure from fusion reactions, gravity begins winning the eternal struggle. The helium core contracts, compressing under the weight of the overlying layers. This contraction releases gravitational energy, heating the core even as it shrinks. The rising temperature affects the hydrogen-rich layer immediately surrounding the core. This shell becomes hot enough for hydrogen fusion to ignite, creating what astronomers call shell burning. Paradoxically, even though the star has exhausted its core hydrogen, it now produces more energy than during its main sequence life. The shell-burning hydrogen generates tremendous amounts of power, far more than the steady core burning that characterized the star's youth. This extra energy has dramatic consequences for the star's structure. The enormous power output pushes the outer layers of the star outward, causing the star to swell. As the radius increases, the surface area grows, and even though each square meter of the surface becomes cooler, the total energy radiated by the star increases due to its vastly expanded size. The star's appearance transforms. The hot, blue photosphere gives way to a cooler, orange-red surface. Betelgeuse transitions from a blue giant to a red supergiant. Meanwhile, the helium core continues contracting and heating. In less massive stars, this process leads to a helium flash, a brief, violent ignition of helium fusion in a degenerate core. But in massive stars like Betelgeuse, the core does not become degenerate. Instead, when the core temperature reaches about 100 million Kelvin, helium fusion ignites smoothly, without the explosive violence of a helium flash. This process, called the triple alpha process, fuses 3 helium-4 nuclei together to form carbon-12. The triple alpha process has a fascinating history and a crucial role in cosmic chemistry. Helium nuclei, or alpha particles as physicists call them, consist of 2 protons and 2 neutrons bound together. When 2 alpha particles collide at sufficient energy, they can briefly form a beryllium-8 nucleus. This nucleus is highly unstable, typically falling apart in less than a trillionth of a second. However, in the dense, hot environment of a stellar core, before the beryllium-8 can decay, another alpha particle may collide with it, forming a stable carbon-12 nucleus. This process seems impossibly unlikely, requiring 3 particles to come together in just the right way at just the right time. Yet it occurs constantly in the cores of red giants and supergiants, creating the carbon that forms the basis of all known life. In the 1950s, physicist Fred Hoyle predicted that for this process to work efficiently enough to explain the observed abundance of carbon in the universe, the carbon-12 nucleus must possess a specific energy level that allows the reaction to proceed. Later experimental work confirmed Hoyle's prediction, revealing a remarkable fine-tuning in the laws of physics that makes carbon, and therefore life, possible. In Betelgeuse's core, helium fusion proceeds for roughly 1 to 2 million years, a brief interlude in the star's life. The core temperature remains at about 180 million Kelvin, sufficient to maintain helium fusion but not high enough to ignite the next stage of fusion. The products of helium fusion, primarily carbon and oxygen, accumulate in the core, forming a carbon-oxygen interior surrounded by a helium-burning shell, which in turn is surrounded by a hydrogen-burning shell. The star has developed an onion-like layered structure, with each shell burning a different fuel. As the helium in the core depletes, the process repeats. The carbon-oxygen core contracts and heats, eventually reaching the 600 million Kelvin needed to ignite carbon fusion. At these extreme temperatures, carbon nuclei can overcome their mutual electric repulsion and fuse together, forming neon, magnesium, and other elements. Carbon burning lasts only about 1,000 years, a cosmic eye blink. The energy release is enormous, but the fuel consumption is correspondingly rapid. When carbon exhausts, the core contracts again, heating to about 1.2 billion Kelvin to ignite neon fusion. Neon burning transforms neon into oxygen and magnesium and lasts only about 1 year. The pace of evolution accelerates dramatically as the star runs through its remaining fuel stages with increasing rapidity. Next comes oxygen fusion at 1.5 billion Kelvin, lasting only about 6 months, and producing silicon, sulfur, and other elements. Finally, at about 2.7 billion Kelvin, silicon begins fusing. But silicon fusion differs from earlier stages. Instead of simply fusing silicon nuclei together, the extreme temperatures cause photons to have enough energy to break apart existing nuclei. These nuclear fragments then recombine in various ways, building up heavier and heavier elements through a complex network of reactions. Over the course of about 1 day, yes, just 1 day, silicon fusion builds elements all the way up to iron and nickel. This creates the final structure of Betelgeuse's interior before the end. The very center consists of an iron-nickel core, surrounded by a thin shell fusing silicon, surrounded by shells burning oxygen, neon, carbon, helium, and hydrogen in succession. Each shell is separated from its neighbors by layers of ash from the reactions above it. The structure resembles an onion, with the different layers representing the stars past fusion stages, all now active simultaneously in different regions. Iron occupies a unique position in nuclear physics. It has the highest binding energy per nucleon of any element, meaning it takes more energy to break apart an iron nucleus than any other nucleus, and conversely, iron formation releases less energy than the formation of lighter or heavier elements. Iron represents the end of the nuclear fusion road. Fusing iron into heavier elements does not release energy, it absorbs energy. When a star's core becomes predominantly iron, it can no longer generate energy through fusion. The nuclear furnace dies. For Betelgeuse, this moment approaches. The star has probably been a red supergiant for about 40,000 years, a brief moment in cosmic time. It may continue in this state for another few tens of thousands of years, though uncertainty in stellar models makes precise predictions impossible. But eventually, within the next 100,000 years, and possibly much sooner, Betelgeuse's iron core will reach a critical mass of about 1.4 solar masses. At this point, gravity will finally overwhelm all other forces. The iron core cannot generate energy through fusion, so nothing can support it against gravitational collapse. In less than a second, the core implodes. The iron nuclei break apart into their constituent protons and neutrons, a process that absorbs enormous amounts of energy and removes the last bit of pressure support. Electrons merge with protons to form neutrons, releasing neutrinos that carry away even more energy. The core collapses from the size of Earth to a ball of neutrons perhaps 20 kilometers across, all in the time it takes to blink. The collapse releases an amount of energy difficult to comprehend. In that 1 second, the collapsing core radiates more energy than all the stars in the observable universe combined. Most of this energy emerges as neutrinos, ghostly particles that barely interact with matter and can escape directly from the core. But about 1% of the energy couples to the overlying layers of the star, heating them to billions of degrees and launching a shock wave that tears through the outer shells. This is a core collapse supernova, specifically a type Roman II supernova, characterized by the presence of hydrogen in the spectrum of the explosion. As the shock wave propagates outward through the star's layers, it heats the material it encounters to extreme temperatures. This triggers explosive nuclear fusion, creating elements that cannot form in normal stellar conditions. The shock wave passes through shells containing silicon, oxygen, carbon, helium, and hydrogen, each reacting violently to the enormous energy input. In the intense environment of the supernova explosion, elements heavier than iron finally form. The rapid influx of neutrons through a process called the R process creates elements all the way up to uranium and beyond. Gold, platinum, thorium, and other heavy elements all form in these few seconds of explosive nucleosynthesis. The supernova ejects these newly formed elements, along with all the products of the star's lifetime of fusion, into the surrounding interstellar medium at velocities of tens of thousands of kilometers per second. The visible display of a supernova represents one of the most spectacular events in the cosmos. For several weeks, a single exploding star can outshine an entire galaxy of billions of normal stars. The supernova brightens rapidly over the first few days as the shock wave reaches the star's surface and the outer layers begin expanding. At peak brightness, which typically occurs about 2 weeks after the explosion, a supernova can reach an absolute magnitude of -17 or brighter, about 400 million times more luminous than the Sun. For Betelgeuse, located only about 650 light-years away, the supernova would be spectacular indeed. At peak, it would reach an apparent magnitude of about -12, roughly as bright as the full moon. The supernova would be easily visible during daylight and would cast shadows at night. It would dominate the night sky for weeks, slowly fading over months as the expanding debris cloud cooled. For about a year, it would remain visible to the naked eye, gradually dimming to binocular and then telescopic visibility. This explosion would not harm Earth. At 650 light-years distance, the radiation from the supernova, while intense, would not damage our atmosphere or threaten life. The dangerous radiation, primarily gamma rays and X-rays, would be absorbed by the upper atmosphere. We might detect a slight increase in cosmic rays reaching Earth's surface as the expanding debris cloud eventually encounters our solar system, but this would pose no significant risk. What remains after the explosion depends on the exact mass of the collapsing core. If the core mass falls between about 1.4 and 3 solar masses, the collapse halts when the core material reaches nuclear density, forming a neutron star. This incredibly dense object, composed almost entirely of neutrons, packs roughly 1.4 solar masses into a sphere only 20 kilometers across. The density is so extreme that a teaspoon of neutron star material would weigh about 1 billion tons. If the core exceeds about 3 solar masses, no force in physics can prevent its continued collapse. The gravity becomes so intense that spacetime itself curves inward, creating a black hole. A stellar mass black hole forms, perhaps 10 to 20 solar masses, surrounded by the expanding supernova remnant. Whether Betelgeuse will leave a neutron star or a black hole depends on details of its interior structure and mass loss history that we cannot yet determine with certainty. The supernova remnant expands into the interstellar medium, sweeping up and shocking the surrounding gas. For thousands of years, the remnant remains visible as an expanding shell of hot gas, gradually fading as it disperses into space. The material ejected by the supernova, enriched with carbon, oxygen, silicon, iron, gold, and all the other products of nucleosynthesis, mixes with the interstellar medium. Eventually, this enriched material becomes incorporated into new molecular clouds, which collapse to form new generations of stars and planets. This cosmic recycling has operated throughout the history of our galaxy. The first stars, born from the primordial hydrogen and helium created in the Big Bang, contained essentially no heavy elements. When these stars exploded, they enriched the interstellar medium with the first carbon, oxygen, and iron. Subsequent generations of stars formed from progressively more enriched material. Our Sun, a relative latecomer, formed about 4.6 billion years ago, inherited the products of countless stellar generations that lived and died before it. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were forged in the cores of ancient stars and scattered into space by supernova explosions. Conclusion: the Hunter's legacy. As we stand beneath the winter sky and trace the familiar pattern of Orion, we witness a constellation in transition. The great dimming of Betelgeuse served as a dramatic reminder that the stars, for all their appearance of permanence, live dynamic lives with beginnings and ends. Betelgeuse's unexpected behavior in 2019 and 2020 demonstrated that red supergiants operate under conditions far more violent and unstable than astronomers previously imagined. The surface mass ejection that caused the great dimming was not a harbinger of immediate supernova doom, but rather a glimpse into the normal, if dramatic, behavior of evolved massive stars. Betelgeuse sheds mass through these episodic ejections, losing perhaps a solar mass every few 100,000 years. This mass loss plays a crucial role in determining the star's ultimate fate. The more mass Betelgeuse loses before its core collapses, the smaller the final remnant will be, affecting whether a neutron star or black hole forms in the explosion's aftermath. The investigation into the Great Dimming revealed the sophistication of modern astronomy and the power of coordinated observation. When Betelgeuse began its dramatic fade, astronomers deployed an arsenal of instruments spanning the electromagnetic spectrum. Ground-based telescopes tracked optical and infrared changes, space telescopes observed in ultraviolet wavelengths impossible to study from Earth's surface, and radio telescopes probed the molecular structure of the star's extended atmosphere. Amateur astronomers contributed crucial data, maintaining continuous monitoring when professional facilities needed to observe other targets. This comprehensive observational campaign produced unprecedented insights into red supergiant physics. The combination of imaging, spectroscopy, photometry, and theoretical modeling allowed researchers to reconstruct the sequence of events that led to the dimming with remarkable detail. The story that emerged, of a violent convective ejection followed by dust formation and photospheric cooling, demonstrated both the complexity of red supergiant atmospheres and the ability of modern astronomy to decipher even subtle stellar behaviors. The event also highlighted gaps in our understanding of stellar evolution. Prior to the Great Dimming, most models of red supergiant mass loss assumed a relatively steady stellar wind, perhaps punctuated by regular pulsation-driven episodes. The violence of the surface mass ejection suggested that episodic, explosive events might contribute more significantly to mass loss than previously believed. This has implications for our understanding of how massive stars evolve and what kinds of progenitors produce different types of supernova. Questions remain about the frequency and triggering mechanisms of such ejections. Did Betelgeuse experience something unusual, or do all red supergiants undergo similar events regularly? If the latter, why haven't we observed more such dimming episodes in other stars? The answers may lie in geometry and timing. The dust cloud from Betelgeuse's ejection happened to pass directly between the star and Earth, creating the dramatic dimming we observed. Other stars may experience similar ejections that we cannot detect, because the dust clouds move in directions that do not intersect our line of sight. The role of pulsation in triggering surface mass ejections deserves further study. Red supergiants typically pulsate with periods ranging from months to years, their surfaces rising and falling in complex patterns. These pulsations may occasionally achieve sufficient amplitude to launch material into space, particularly if multiple pulsation modes interact constructively. Understanding this connection requires long-term monitoring of many red supergiants, correlating pulsation behavior with mass loss episodes. Betelgeuse's place within the larger context of the Orion constellation adds another layer to the story. The constellation serves as a laboratory for studying stellar evolution across a wide range of masses and ages. The three belt stars, Alnitak, Alnilam, and Mintaka, shine as young, hot O and B-type giants, stars still fusing hydrogen in their cores and displaying the blue-white colors characteristic of high surface temperatures. These stars formed relatively recently, perhaps only a few million years ago, from the same giant molecular cloud complex that continues to spawn new stars in the Orion Nebula. Rigel, the brilliant blue-white star marking Orion's left foot, represents another massive star, though one younger than Betelgeuse. With a luminosity of about 120,000 times that of our Sun and a surface temperature of 11,000 Kelvin, Rigel burns with fierce intensity. This star likely has several million years remaining before it exhausts its core hydrogen and begins its evolution toward the red supergiant phase. When that time comes, Rigel will swell to enormous size, perhaps rivaling or exceeding Betelgeuse's current dimensions. The contrast between Betelgeuse and Rigel illustrates different stages in the life cycle of massive stars. Rigel represents vigorous youth, burning its nuclear fuel at a prodigious rate, but still in the stable main sequence phase. Betelgeuse shows us old age, a star that has burned through its hydrogen, swollen to vast proportions, and now approaches the catastrophic end that awaits all massive stars. Yet both will share the same ultimate fate: core collapse and supernova explosion, each returning its enriched material to the interstellar medium. Below Orion's belt lies the Orion Nebula, designated M42 in astronomical catalogues. This fuzzy patch of light, visible to the naked eye on dark nights, represents one of the most productive star-forming regions in our vicinity. The nebula spans roughly 24 light-years across and contains enough raw material to form thousands of stars. Within its dusty embrace, young stars are being born right now, their formation driven by the same gravitational forces that created Betelgeuse millions of years ago. Infrared observations of the Orion Nebula reveal clusters of protostars, objects still in the process of collapsing and heating toward the temperatures needed to ignite hydrogen fusion. Some of these protostars already show developing protoplanetary disks, flattened clouds of gas and dust from which planets will eventually form. In perhaps a few million years, some of these protostars may become massive blue giants similar to the belt stars we see today. Billions of years from now, if any of them possess sufficient mass, they too will evolve into red supergiants and explode as supernova. This ongoing cycle of stellar birth, life, and death has operated throughout the Milky Way's history. Our galaxy formed approximately 13.6 billion years ago, not long after the Big Bang itself. The first generation of stars, called population Roman 3 stars, formed from pure hydrogen and helium, the only elements created during the Big Bang. These stars, likely much more massive than anything we see today, lived brief lives and exploded as the universe's first supernova, enriching the interstellar medium with the first heavy elements. Subsequent stellar generations formed from progressively more enriched material. Astronomers classify stars into populations based on their metallicity, the abundance of elements heavier than helium. Population Roman 3 stars have essentially zero metallicity. Population Roman 2 stars, found primarily in globular clusters and the galactic halo, have low metallicity, typically only 1% of the solar value. Population I stars, like our Sun and most of the stars we see in the night sky, have much higher metallicity, reflecting their formation from material enriched by many previous stellar generations. Betelgeuse belongs to population I, born from material that had already been processed through numerous cycles of stellar nucleosynthesis. The carbon, oxygen, silicon, and iron present in Betelgeuse when it formed came from ancient supernova that exploded billions of years ago. When Betelgeuse explodes, it will add its own contribution to this ongoing enrichment, creating a new generation of heavy elements that will eventually become incorporated into future stars and planets. The study of stellar nucleosynthesis and galactic chemical evolution represents one of astronomy's great success stories. The theory, developed primarily in the 1950s and 1960s by physicists including Fred Hoyle, Margaret Burbidge, Geoffrey Burbidge, and William Fowler, explained how stars create elements through nuclear fusion and how supernovae distribute these elements throughout galaxies. This work earned Fowler the Nobel Prize in Physics in 1983, though many felt Hoyle's omission from the prize was unjust. The theory's predictions have been spectacularly confirmed through astronomical observations. By analyzing the spectra of stars of different ages and metallicities, astronomers have traced the chemical evolution of our galaxy over billions of years. The oldest stars show deficiencies in elements heavier than helium, exactly as expected if they formed before substantial supernova enrichment occurred. Younger stars show progressively higher abundances of heavy elements, reflecting the cumulative contributions of supernova over galactic history. Our own solar system provides a detailed record of this enrichment process. Meteorites, rocky debris left over from the solar system's formation, contain tiny grains of presolar material, dust grains that formed around other stars and were incorporated into the solar nebula. By analyzing the isotopic composition of these grains, scientists can identify their stellar sources. Some grains show isotopic signatures characteristic of red giant stars, others come from supernova, and still others formed in the winds of dying sun-like stars. The solar system, assembled from debris contributed by many different stellar sources, each adding its unique chemical signature. The realization that we are literally made of stardust, that the atoms in our bodies were forged in the nuclear furnaces of long-dead stars, ranks among the most profound insights in all of science. Every breath we take contains oxygen atoms that once resided in the core of a red giant. The calcium in our bones was synthesized through silicon burning in a massive star's final days. The iron in our blood formed through the complex nuclear reactions of silicon fusion. We are not separate from the cosmos, but intimately connected to it through the cycle of stellar birth and death. Betelgeuse's eventual supernova will continue this ancient cycle. When the star explodes, it will eject several solar masses of enriched material into the interstellar medium at velocities exceeding 10,000 kilometers per second. This material will collide with the surrounding gas, creating a shock wave that sweeps up and compresses the interstellar medium. Over thousands of years, the expanding supernova remnant will slow as it entrains more and more material, eventually dispersing its contents across hundreds of light years. Some of this material will become incorporated into new molecular clouds, setting the stage for future star formation. When these clouds collapse under gravity, they will form a new generation of stars enriched with Betelgeuse's contribution to the cosmic chemical inventory. Perhaps hundreds of millions of years from now, planets will form around some of these stars, and on some of those planets, life may arise, built from atoms that once resided in Betelgeuse's core. The timescale of Betelgeuse's remaining life remains uncertain. Red supergiant evolution depends sensitively on factors like the star's exact mass, its rotation rate, its mass loss history, and the detailed structure of its core. Different stellar evolution models produce different predictions for when Betelgeuse will explode. Some models suggest the star could detonate anytime within the next few thousand years, while others predict it may remain stable for 100,000 years or more. This uncertainty stems partly from our incomplete understanding of mass loss in red supergiants. The rate at which Betelgeuse sheds material affects how quickly its core approaches the critical iron mass that triggers collapse. If mass loss proceeds primarily through steady stellar winds, the evolution proceeds relatively smoothly and predictably. If episodic surface mass ejections like the one that caused the Great Dimming dominate, the evolution becomes more stochastic and harder to predict. The star's rotation also matters. Many massive stars rotate rapidly, their surfaces moving at hundreds of kilometers per second. Rotation affects the star's structure and evolution in complex ways. It can mix material between different layers, bringing fusion products to the surface and fresh fuel to the core. It influences the geometry of stellar winds and mass loss. Fast rotation can even prevent the formation of a red supergiant altogether, instead producing stars called Wolf-Rayet stars that strip away their hydrogen envelopes and expose their helium cores. Whether Betelgeuse rotates significantly remains unclear. Direct measurements of surface rotation are difficult for red supergiants due to their large size and the complexity of their atmospheres. The presence of enormous convection cells and the thick, turbulent atmosphere make it challenging to track surface features with sufficient precision to determine rotation rates. Some evidence suggests Betelgeuse rotates slowly, perhaps taking several decades to complete one rotation, but considerable uncertainty remains. The possibility of a companion star adds another layer of complexity. Many massive stars form in binary or multiple star systems, and companions can significantly influence stellar evolution. A companion star can strip material from a red supergiant, altering its mass loss rate and potentially affecting when and how it explodes. Some observations have suggested Betelgeuse might have a companion, but this remains unconfirmed and controversial. If Betelgeuse does harbor a companion, the supernova explosion would have dramatic consequences for that companion star. The explosion would subject it to intense radiation and a blast wave of high-velocity ejecta. Depending on the companion's distance and mass, it might survive the explosion, perhaps ending up as a runaway star traveling through the galaxy at high velocity. Alternatively, the explosion might disrupt the companion entirely or trigger its own premature evolution and explosion. These uncertainties make it impossible to predict exactly when Betelgeuse will explode. Astronomers can only say with confidence that the explosion will occur sometime within the next 100,000 years and possibly much sooner. Given that the star is already 550 to 700 light-years away, and given that we see it not as it is now, but as it was centuries ago, the explosion may have already occurred. Betelgeuse might have detonated during the Renaissance, or during the American Revolution, or last Tuesday, and the light from that explosion is still racing toward Earth at 300,000 kilometers per second, due to arrive at some unknown future date. This temporal disconnect adds a philosophical dimension to observing Betelgeuse. We watch a star that may already be dead, its light a ghost signal from the past. When we finally witness the supernova, we will see an explosion that occurred centuries ago, an event already ancient by the time the light reaches our telescopes. Time and space intertwine in cosmology in ways that defy everyday intuition. The scientific value of observing a nearby supernova cannot be overstated. The last supernova visible to the naked eye in our galaxy occurred in 1604, observed by Johannes Kepler and many others. That explosion, now called Kepler's supernova or SN 1604, appeared in the constellation Ophiuchus and reached a peak brightness of magnitude -2.5, brighter than Jupiter. For 3 weeks, it remained visible during daylight, and observers could track it for over a year until it faded below naked eye visibility. Before that, in 1572, Tycho Brahe observed another bright supernova in Cassiopeia, now called Tycho's supernova or SN 1572. This explosion reached magnitude -4, brighter than Venus, and profoundly influenced Brahe's astronomical work. The observation that a new star could appear in what was supposed to be the unchanging celestial sphere challenged prevailing Aristotelian cosmology and contributed to the scientific revolution. Both of these historical supernovae occurred before the invention of the telescope and at distances of 10,000 to 20,000 light-years, far enough that detailed observations were impossible. Betelgeuse, at only 650 light-years, would provide an unprecedented opportunity to study a supernova with modern instruments. Telescopes spanning the electromagnetic spectrum would observe the explosion from the moment the shock wave breaks through the stellar surface until the remnant fades thousands of years later. The first sign of the explosion would be a burst of neutrinos, detected by neutrino observatories around the world within minutes of core collapse. These ghostly particles, which barely interact with matter, would pass through Earth almost unhindered, but sensitive detectors buried deep underground would register a handful of these neutrinos, providing direct evidence of the core collapse before the light reaches us. Hours later, the shock wave would reach the star's surface, and the supernova would begin to brighten rapidly in visible light. Astronomers would mobilize observatories worldwide and in space to capture every phase of the explosion. Optical and ultraviolet telescopes would track the brightening, recording spectra that reveal the composition and velocity of the expanding debris. X-ray and gamma-ray telescopes would detect high-energy radiation from the shock-heated material. Radio telescopes would observe the interaction between the expanding remnant and the surrounding interstellar medium. Infrared telescopes would peer through any dust in the vicinity to observe the inner regions of the remnant. The data collected would revolutionize our understanding of supernova physics. We would observe directly how shock waves propagate through a red supergiant's layered structure, how different elements mix in the explosion, and how the remnant evolves in the immediate aftermath. We would test theories of supernova mechanism, the detailed physics of how core collapse converts gravitational energy into an explosion. We would observe the formation of the neutron star or black hole remnant and study its properties. Beyond the scientific value, a Betelgeuse supernova would captivate public imagination worldwide. The appearance of a new star brighter than the Moon would be impossible to miss and would generate intense interest in astronomy and science. For several weeks, Betelgeuse would dominate the night sky, outshining every other star and remaining visible even in light-polluted cities. People around the world would look up and witness cosmic violence occurring on a scale difficult to comprehend, a reminder of the dynamic, ever-changing nature of the universe. The cultural impact would likely equal or exceed that of historical supernova. The 1054 supernova that created the Crab Nebula was recorded by Chinese, Japanese, and Arab astronomers, and possibly by Native Americans in what is now New Mexico. The 1572 and 1604 supernova profoundly influenced European astronomy and philosophy. A Betelgeuse supernova in the 21st century, observed with modern instruments and shared instantly through global communications networks, would create a shared human experience of cosmic significance. The constellation Orion would be permanently transformed. For thousands of years, humans have recognized the pattern of the hunter, marked by Betelgeuse at his eastern shoulder. After the supernova, that bright red star would be gone, replaced by a gradually fading point of light as the supernova remnant cooled and dispersed. Future generations would look up at Orion and see a different pattern, a hunter missing his distinctive red shoulder star. The constellation's appearance, familiar for all of recorded human history, would change within a human lifetime. Yet this transformation would also serve as a reminder of the cosmos's dynamic nature. The night sky, which appears unchanging on human timescales, actually churns with constant activity when viewed over longer periods. Stars are born, evolve, and die. Constellations slowly change shape as stars move through space with different velocities. Over hundreds of thousands of years, even familiar patterns like the Big Dipper and Orion become unrecognizable as their component stars drift apart. The impermanence of celestial objects connects to broader themes in astronomy and cosmology. Nothing in the universe lasts forever. Stars form from diffuse gas, burn for millions or billions of years depending on their mass, and eventually exhaust their fuel and die. Galaxies collide and merge, transforming through these violent interactions. Even the universe itself has a finite age, having emerged from the Big Bang approximately 13.8 billion years ago, and faces an uncertain future as expansion continues. This cosmic perspective places human existence in a vast context of space and time. We live on a small planet orbiting an ordinary star in the outer reaches of a typical galaxy, one of hundreds of billions of galaxies in the observable universe. Our species has existed for perhaps 300,000 years, our civilization for less than 10,000 years, a tiny fraction of cosmic history. Yet despite our insignificance in space and time, we possess the capacity to understand the cosmos, to decipher the physical laws that govern stellar evolution and galactic dynamics. The study of Betelgeuse and other red supergiants exemplifies this capacity for understanding. Through careful observation and theoretical analysis, astronomers have pieced together the life story of these massive stars, from their formation in molecular clouds through their brief but brilliant lives to their catastrophic deaths as supernova. We understand the nuclear physics that powers their fusion reactions, the fluid dynamics of their convective envelopes, and the complex processes that drive their mass loss and eventual collapse. This understanding derives from a combination of observation, theory, and increasingly sophisticated computer modeling. Modern stellar evolution codes simulate the entire life of a star by solving the equations of stellar structure, following the nuclear reactions in the core, tracking energy transport through radiation and convection, and modeling mass loss through stellar winds. These codes, run on powerful supercomputers, can reproduce observed stellar properties and predict future evolution with impressive accuracy. Yet gaps in our understanding remain. The Great Dimming revealed that red supergiant atmospheres behave in more complex and violent ways than standard models predicted. The formation of dust in stellar outflows, the triggering mechanism for surface mass ejections, the detailed physics of convection in extremely low-density stellar envelopes, all these phenomena require further study. Each new observation of Betelgeuse and other red supergiants helps constrain theoretical models and improve our understanding. The future of Betelgeuse studies looks bright. Next-generation telescopes currently under construction or in planning phases will enable unprecedented observations of red supergiants. The extremely large telescope, with its 39-meter primary mirror, will resolve details on Betelgeuse's surface smaller than the current generation of interferometers can achieve. The James Webb Space Telescope, already in operation, brings unprecedented infrared sensitivity to bear on problems like dust formation in stellar winds. New neutrino detectors coming online will be ready to capture the neutrino burst when Betelgeuse finally explodes. Ground-based interferometry continues to improve as well. Facilities like the Chara Array and VLTI can now directly image stellar surfaces for nearby giant stars, revealing convection patterns, dark spots, and asymmetries. These observations provide crucial tests of theoretical models and help astronomers understand the physical processes operating in red supergiant atmospheres. As techniques improve and sensitivity increases, we will gain ever more detailed views of these fascinating objects. Amateur astronomers also play a vital role in monitoring Betelgeuse and other variable stars. Organizations like the American Association of Variable Star observers coordinate worldwide observations, creating long-term databases of stellar brightness measurements. When the Great Dimming occurred, amateur observers provided crucial continuous coverage that professional facilities, with their limited observing time, could not match. This collaboration between professional and amateur astronomers enriches the science and engages a broader community in astronomical research. The broader implications of red supergiant research extend beyond stellar astrophysics. Understanding how massive stars evolve and explode matters for many fields of astronomy. Supernova explosions influence galaxy evolution by injecting energy and enriched material into the interstellar medium. This feedback can trigger or suppress star formation, affecting how galaxies develop over cosmic time. Supernova also serve as standard candles for measuring cosmic distances, a technique that led to the discovery of the universe's accelerating expansion and dark energy. The heavy elements produced in supernova make possible the chemistry of life. Carbon, nitrogen, oxygen, phosphorus, sulfur, and many other biologically essential elements form primarily in massive stars and get distributed through supernova explosions. The iron in hemoglobin, the calcium in bones, the sodium and potassium ions that enable nerve signals, all originated in stellar nucleosynthesis. Without generations of massive stars living and dying, the complex chemistry required for life could not exist. This connection between stellar evolution and biological existence raises profound questions about our place in the cosmos. We are not merely observers of the universe, but participants in cosmic evolution, structures of organized complexity that emerged from the same processes that form stars and galaxies. The atoms in our bodies participated in countless cosmic cycles before assembling into the molecules of life. We are, quite literally, the universe becoming aware of itself. Betelgeuse, in its current red supergiant phase, represents a crucial node in this cosmic cycle. The star has already created vast amounts of carbon, oxygen, silicon, and other heavy elements through successive stages of nuclear fusion. When it explodes, these elements will spread through the interstellar medium, becoming available for incorporation into future stellar systems. Some of this material may eventually become part of planets orbiting stars yet to form, and on some of those planets, given the right conditions, life may arise. The contemplation of such vast scales of space and time, from the microscopic realm of nuclear fusion to the galactic scales of supernova remnant dispersion, from the human lifespan to the billions of years of cosmic evolution, induces what astronomers sometimes call the cosmic perspective. This viewpoint recognizes both the vastness of the universe and the significance of our ability to comprehend it. We are tiny, yes, but we are also remarkable, the product of 13.8 billion years of cosmic evolution that has produced structures capable of understanding their own origins. Looking up at Orion on a winter night, we see this cosmic story written in light. The young blue giants of the belt and the ancient red supergiant Betelgeuse represent different chapters in the life cycle of massive stars. The Orion Nebula shows a stellar birth, while Betelgeuse approaches stellar death. Together, these objects illustrate the dynamic nature of the cosmos, the endless cycle of creation and destruction that has operated throughout cosmic history and will continue far into the future. The specific moment when Betelgeuse will explode remains unknown, hidden from us by the limitations of our theoretical understanding and the light travel time between the star and Earth. We can only watch, monitor, and wait, ready to observe when nature decides to reveal this spectacular event. Every night that Betelgeuse shines in Orion's shoulder, we see a star in its final act, a massive sun that could explode at any moment or continue burning for thousands of years more. This uncertainty adds to the fascination. Betelgeuse represents both the known and the unknown in astronomy. We understand the basic physics of red supergiants, the nuclear reactions that power them, and the gravitational collapse that will end them. Yet we cannot predict with precision when any individual star will reach its end point. We must content ourselves with probabilistic statements and ranges of possibilities, acknowledging the limits of our knowledge while celebrating how much we have learned. The Great Dimming episode demonstrated both our capabilities and our limitations. We successfully explained the observed phenomenon through a combination of observation and theory, piecing together the story of a surface mass ejection and dust cloud formation. Yet the event surprised us. Current models did not predict such dramatic mass loss episodes. This combination of understanding and surprise characterizes the scientific enterprise at its best, as we continually refine our models in response to new observations. As we conclude this exploration of Orion and Betelgeuse, several key themes emerge. First, the interconnectedness of cosmic phenomena. Stellar evolution links to chemical evolution links to the possibility of life. Second, the power of scientific methodology to reveal deep truths about nature through observation, theory, and modeling. Third, the dynamic nature of the cosmos, constantly changing even though many changes occur on timescales far longer than human lifetimes. Fourth, the remarkable fact that we, as conscious beings, can comprehend these cosmic processes and trace our own origins back through billions of years of evolution. Betelgeuse will explode someday, perhaps tomorrow, perhaps 100,000 years from now. When it does, it will briefly become one of the brightest objects in the sky, a beacon visible across interstellar space. The explosion will forge elements that cannot form in any other environment, distributing them through space to become part of future stellar systems. The remnant left behind, whether neutron star or black hole, will serve as a monument to the star that was, a dense relic of gravitational collapse. But until that moment arrives, Betelgeuse continues its vigil in Orion's shoulder, a red beacon in the winter sky. It pulses with a roughly 420-day rhythm, its surface rising and falling as it burns helium in its core. Massive convection cells churn its outer layers, occasionally launching violent eruptions like the one that caused the Great Dimming. Dust forms in its extended atmosphere and stellar wind carries material into space, gradually whittling away the star's outer envelope. Deep in the core, fusion reactions proceed through carbon, neon, oxygen, and eventually silicon, building an iron core that grows inexorably toward the critical mass that triggers collapse. All of this happens 650 light-years away, in a region of space we can observe but never visit with current technology. The light we see tonight left Betelgeuse in the 1370s or thereabouts, during the late medieval period on Earth. If Betelgeuse exploded at this moment, we would not know for another 650 years, long after everyone currently alive had passed away. This temporal disconnect between events and observations creates a strange relationship between us and the stars we study, as we peer into the past and attempt to infer the present. The constellation Orion, with Betelgeuse at its shoulder, connects us to the long history of human civilization and to the even longer history of the cosmos. Ancient Egyptians saw Orion as Osiris, lord of the underworld. Greeks saw a great hunter placed in the sky by Zeus. Arabs saw a giant, his hand marked by the bright red star. Indigenous peoples around the world recognized these same stars and incorporated them into their own myths and stories. For all of recorded history, and probably long before, humans have looked up at these stars and wondered about their nature. Now, in the 21st century, we have answers to many of those ancient questions. We know what stars are made of, how they generate energy, and how they evolve over time. We can calculate the temperature and luminosity of Betelgeuse, estimate its mass and radius, and predict its ultimate fate. We have imaged its surface, analyzed its spectrum, and modeled its interior structure. The mystery remains, but we have pushed back the boundaries of the unknown, illuminating previously dark corners with the light of scientific understanding. Yet the wonder remains undiminished. Understanding the physics of red supergiants does not make them less magnificent. If anything, comprehension enhances appreciation. Knowing that Betelgeuse is a dying star hundreds of times larger than the Sun, that it generates energy through the fusion of helium into carbon and oxygen, that it will someday explode with the brightness of billions of stars. All of this knowledge adds layers of meaning to the simple act of looking up and seeing that red point of light in Orion's shoulder. The hunter watches over the winter sky, his form outlined by young blue giants and an aging red supergiant, with the stellar nursery of the Orion Nebula hanging from his belt. This celestial pattern has guided travelers, marked seasons, and inspired countless stories across millennia. It will continue to shine for thousands of years more, though perhaps not in exactly the same configuration. When Betelgeuse finally explodes, Orion will be transformed, and a new chapter in human astronomical understanding will begin. Until that moment, we watch and wait, monitoring the star with increasingly sophisticated instruments, refining our models of stellar evolution, and preparing for the supernova that will inevitably come. The Great Dimming gave us a preview of red supergiant violence, a glimpse into the turbulent conditions that characterize these evolved massive stars. Future observations will undoubtedly reveal more surprises as Betelgeuse continues its erratic behavior, pulsating, ejecting material, and slowly building toward the final catastrophe. The story of Betelgeuse is ultimately the story of cosmic evolution writ small, the life and death of a single star against the backdrop of galactic history. It is a story of nuclear physics and fluid dynamics, of gravity and thermodynamics, of observation and theory. It is a story that connects the largest structures in the cosmos to the smallest particles, linking the expansion of stellar envelopes to the fusion of atomic nuclei in stellar cores. And it is a story that includes us as observers and participants in the grand cosmic drama. Every photon of light that reaches our eyes from Betelgeuse carries information about the star's current state, encoded in wavelength, intensity, and polarization. Every spectrum reveals details of composition, temperature, and velocity. Every image shows structure, asymmetry, and change. Astronomers decode this information, converting raw data into physical understanding, building models that explain observations and make predictions about future behavior. This process of scientific investigation continues daily as telescopes around the world monitor Betelgeuse and other red supergiants, gathering data that advances our understanding of stellar evolution. The technological capability that enables this investigation represents centuries of development, from Galileo's first telescopic observations to modern interferometers that can resolve details smaller than the star's disk. Each advance in technology has brought new revelations, from the discovery of stellar spectra revealing composition to radio observations detecting molecules in stellar winds to direct imaging of convection cells on stellar surfaces. The next generation of instruments will push these capabilities even further, perhaps finally allowing us to predict with confidence when Betelgeuse will reach its end. But prediction is not the only goal. Understanding matters as much as prediction, perhaps more. We seek to comprehend the physical processes that drive stellar evolution, to explain why stars behave as they do, and to connect individual stellar phenomena to the broader context of cosmic evolution. Betelgeuse serves as a laboratory for testing our theories, a real-world system that must match our models if those models accurately represent physical reality. When observations and theory disagree, as they did during the Great Dimming, we must refine our understanding, adjusting models to account for newly discovered phenomena. This iterative process of observation, theory, prediction, and refinement characterizes all of science, but astronomy faces unique challenges. We cannot perform controlled experiments on stars, cannot manipulate their properties or run them through different scenarios to see what happens. We can only observe, sometimes over decades or centuries, gathering data as nature presents it. This limitation makes each astronomical event precious, each supernova or stellar merger a unique opportunity to test theories against reality. When Betelgeuse explodes, it will provide such an opportunity on a spectacular scale. The observations made during and after that explosion will test our understanding of supernova physics, nucleosynthesis, shock propagation, and neutron star or black hole formation. They will provide data that cannot be obtained any other way, revealing details of stellar death that we can currently only infer from models. Every aspect of modern astronomy, from observational technique to theoretical modeling to computational simulation, will contribute to studying this event. The anticipation of this explosion drives continued interest in Betelgeuse and other red supergiants. Astronomers maintain monitoring programs ready to alert the community when changes occur. Alert networks stand prepared to coordinate observations when the supernova finally happens. Major observatories have contingency plans for rapid response, ensuring that the explosion will be observed across the electromagnetic spectrum from the moment it becomes visible. Amateur astronomers remain vigilant, knowing that they might be the first to notice the brightening that signals the start of the explosion. This state of preparedness reflects the importance astronomers place on nearby supernova. The last naked-eye supernova in our galaxy occurred over 400 years ago, before modern instruments existed. The 1987 supernova in the Large Magellanic Cloud, visible from the southern hemisphere, provided valuable data but occurred 168,000 light-years away, far enough to limit what could be observed. Betelgeuse, at less than 1% of that distance, would offer an unprecedented view of a supernova explosion, close enough to observe in exquisite detail but far enough to pose no danger to Earth. The scientific papers that will emerge from a Betelgeuse supernova number in the thousands, as researchers analyze every aspect of the explosion and its aftermath. Decades of observations will follow, tracking the expanding remnant as it interacts with the surrounding interstellar medium, monitoring the central compact object as it cools and spins, and searching for evidence of nucleosynthesis products in the ejected material. Graduate students not yet born will write their dissertations on data collected from this single event. Beyond the immediate scientific value, a Betelgeuse supernova would serve educational and cultural purposes. The explosion would provide a teaching opportunity unlike any in recent history, allowing educators to illustrate stellar evolution with a real-time example visible to everyone. The event would capture media attention worldwide, bringing astronomy to front pages and evening news broadcasts. Public interest in science might surge as people engage with one of nature's most spectacular phenomena unfolding before their eyes. The historical record of the supernova would extend beyond scientific papers and news articles. Artists would create works inspired by the brilliant new light in the sky. Photographers would capture images of the supernova alongside earthly landscapes and cityscapes. Musicians might compose pieces commemorating the event. Writers would incorporate it into novels and poems. The supernova would enter human culture as a shared experience, a moment when people around the world looked up at the same celestial event and pondered their place in the cosmos. Religious and philosophical interpretations would inevitably emerge. Some might see the supernova as a sign or portent, reading meaning into the cosmic coincidence of observing such an explosion during their lifetimes. Others might reflect on impermanence and change, on the fact that even stars, those seemingly eternal lights in the sky, have beginnings and ends. Still others might focus on the creative aspect, on how stellar death feeds stellar birth, destruction enabling creation in an endless cosmic cycle. These diverse responses would reflect the human tendency to find meaning in natural phenomena. Throughout history, astronomical events have carried cultural significance beyond their physical causes. Solar eclipses, comets, conjunctions of planets, all have been interpreted through cultural and religious frameworks. A supernova as bright as the moon would certainly generate similar responses, layering cultural meaning atop scientific understanding. Yet the scientific understanding itself offers a kind of meaning, a narrative of cosmic evolution that connects past, present, and future. We understand that the atoms in our bodies originated in stellar furnaces, that we are literally composed of processed stellar material. We know that the Sun and Earth formed from the debris of previous stellar generations, that our existence depends on billions of years of cosmic evolution. A supernova makes this abstract knowledge concrete, showing us the mechanism through which new elements enter the cosmic ecosystem. The philosophy of cosmology grapples with questions about humanity's relationship to the universe. Are we significant or insignificant, observers or participants, the product of random chance or inevitable outcome of cosmic evolution? A Betelgeuse supernova would not answer these questions definitively, but it would provide a framework for contemplating them. Here would be a star vastly larger and more massive than our Sun, meeting its violent end through processes we can understand and predict. The event would occur regardless of human observation, yet our ability to observe and comprehend it gives us a unique place in the cosmic order. The multiverse hypothesis, currently popular in theoretical physics, suggests that our universe might be one of many, perhaps infinitely many, universes with different physical laws and constants. In such a framework, the question of significance shifts. We exist in this particular universe because its physical constants allow for star formation, nucleosynthesis, and ultimately the chemistry of life. Other universes in the multiverse might not support such processes. Observing a supernova reminds us that we live in a universe where these extraordinary events occur, where stars can form, evolve, and die, enriching their environments with heavy elements. Whether or not the multiverse exists, we can say with certainty that we inhabit a universe of extraordinary richness and complexity. Betelgeuse, a single star among hundreds of billions in the Milky Way, among hundreds of billions of galaxies in the observable universe, nevertheless commands our attention and rewards our study. The star's eventual explosion will illuminate fundamental physics, contribute to ongoing chemical evolution, and inspire wonder in those who witness it. In this way, a single stellar death participates in the grand story of cosmic evolution, the story that includes everything from the Big Bang to the present moment. The question of whether intelligent life exists elsewhere in the universe remains unanswered. Decades of searching have not yet revealed definitive evidence of extraterrestrial intelligence, though the search continues. If other civilizations exist within a few thousand light-years of Earth, they too might observe Betelgeuse's supernova, seeing the explosion from their own vantage points in the galaxy. Perhaps they would wonder, as we do, whether other beings might be watching the same event. Perhaps they would use similar physics and mathematics to understand what they observe. Or perhaps their understanding would differ from ours in ways we cannot imagine. The universality of physical law suggests that any technological civilization would develop similar understanding of stellar evolution, even if expressed in different terms. The nuclear physics that powers stars operates the same way everywhere in the universe. Gravity follows the same inverse square law across cosmic distances. Light propagates at the same speed through vacuum regardless of location. These fundamental principles transcend cultural or biological differences, providing a common foundation for understanding nature. This universality makes astronomy a uniquely objective science. While human culture and psychology influence what questions we ask and how we interpret answers, the phenomena we study exist independent of human observation. Betelgeuse would evolve through its life cycle, whether or not intelligent observers existed to watch. Supernova would explode throughout the universe, regardless of whether anyone understood the physics. Our understanding connects us to physical reality, allows us to participate intellectually in cosmic evolution, but does not alter that evolution. The humility appropriate to this realization balances the pride we might feel in our scientific achievements. We have decoded the life cycle of stars, yes, but we did not invent that life cycle. We have calculated the physics of nuclear fusion, but we did not create the underlying laws that make fusion possible. We observe and understand remarkable achievements for a species that evolved on a small planet orbiting an ordinary star, but we remain observers and understanders, not creators or controllers of cosmic processes. This perspective aligns with a scientific worldview that values observation, evidence, and rational analysis over dogma or received wisdom. The history of astronomy shows a progression from mythological explanations of celestial phenomena to increasingly accurate physical understanding. Ancient peoples saw gods and heroes in the stars. We see nuclear physics and gravitational dynamics. Neither view is complete, as the psychological and cultural meanings that humans attach to astronomical phenomena matter for human life, even if they do not describe physical reality. The integration of scientific understanding with humanistic meaning-making represents an ongoing challenge for modern culture. How do we acknowledge both the objective reality revealed by science and the subjective meanings that give life purpose and direction? A Betelgeuse supernova would highlight this challenge, being simultaneously a physical event describable through equations and a meaningful experience for those who witness it. The explosion would be both impersonal, the inevitable consequence of stellar physics, and personal, an event occurring during our lifetimes that connects us to cosmic processes. Perhaps the resolution lies in recognizing that different kinds of questions require different kinds of answers. Science answers how and what questions. How do stars generate energy? What causes supernova? But science does not necessarily answer why. Questions in the teleological sense. Why do we exist? What is the purpose of the universe? These latter questions, if they have answers at all, come from philosophy, religion, or personal reflection rather than scientific investigation. Yet science can inform these deeper questions even if it cannot answer them definitively. Understanding our cosmic origins, recognizing our connection to stellar nucleosynthesis, appreciating the vast scales of space and time. All of these scientific insights provide context for philosophical and religious reflection. A person contemplating the meaning of existence, while aware of cosmic evolution, thinks differently than someone without that awareness, even if their ultimate conclusions might be similar. Betelgeuse, in its role as both physical object and cultural icon, embodies this intersection of scientific and humanistic understanding. The star is a red supergiant approximately 764 solar radii in diameter, fusing helium into carbon and oxygen at about 180 million Kelvin, losing mass at roughly 10·6 solar masses per year through stellar winds. These are physical facts, measurable and quantifiable. But Betelgeuse is also a distinctive red star marking Orion's shoulder, a beacon that has guided travelers and inspired stories for millennia, a celestial marker of winter for northern observers. These cultural facts matter too, not for understanding stellar physics, but for understanding the human relationship to the cosmos. The two kinds of understanding complement rather than compete. Knowing the physics of Betelgeuse enriches appreciation of its cultural significance. Knowing its cultural history adds human dimension to physical facts. The best science communication recognizes both dimensions, presenting accurate physical information while acknowledging the wonder and meaning that astronomical phenomena inspire. A Betelgeuse supernova would demand this kind of comprehensive communication, as scientists would need to explain not just the physics, but also the significance of witnessing such a rare event. The rarity itself deserves emphasis. Core-collapse supernovae occur in the Milky Way roughly twice per century on average, but most happen at large distances or behind obscuring dust clouds, rendering them invisible from Earth. The last nearby, easily visible supernova in our galaxy occurred in 1604, over 4 centuries ago. Several generations of astronomers have lived entire careers without witnessing a naked-eye supernova in the Milky Way. The 1987 supernova in the Large Magellanic Cloud, though visible to the naked eye, appeared only from southern latitudes and as a relatively faint star, not the brilliant beacon that Betelgeuse would become. A Betelgeuse supernova would represent not just a scientific opportunity, but a generational experience, a once-in-several-lifetimes event that those who witness it would remember forever. Parents would take children outside to see the supernova, creating memories that might inspire the next generation of astronomers and scientists. Teachers would adjust lesson plans to incorporate the unfolding event, using real-time observations to illustrate stellar evolution. Amateur astronomers would spend nights tracking the supernova's brightness changes, contributing to the scientific record while experiencing the thrill of observing cosmic violence. The social media age would ensure that images and observations of the supernova spread rapidly around the world. Within hours of the initial brightening, photographs would appear on every platform as people shared their views of the extraordinary new light in the sky. Scientists would use these platforms to explain what was happening, conducting real-time science communication on an unprecedented scale. Misinformation would surely spread as well, requiring constant correction, but overall the event would provide an opportunity for productive public engagement with astronomy. The economic impact might also be significant. Telescope sales would likely surge as people sought to observe the supernova in detail. Planetariums and observatories would host special viewing events, potentially attracting millions of visitors. Travel to dark sky locations might increase as people sought to escape light pollution for better views. Books and documentaries about the supernova would proliferate. The event would generate economic activity alongside scientific and cultural impacts, another dimension of how a cosmic event can reverberate through human society. Yet amid all this attention and activity, the fundamental physical process would proceed according to the laws of nature, indifferent to human observation. The neutron star or black hole formed in the collapse would cool and spin according to the physics of dense matter. The expanding debris would collide with the surrounding interstellar medium, creating shock waves and heating gas to millions of degrees. newly synthesized elements would begin dispersing through space, beginning their long journey to eventual incorporation in new stellar systems. The universe would continue its evolution, as it has for 13.8 billion years and will for trillions of years more. This continuation reminds us that while a supernova is dramatic and significant, it is also ordinary from a cosmic perspective. Supernovae explode throughout the universe constantly, approximately 1 per second across all galaxies combined. Each explosion follows similar physics, generates similar energy output, and produces similar distributions of heavy elements. Betelgeuse would be special to us because of proximity and visibility, but it would be just one of countless supernovae occurring throughout cosmic history. This dual nature, both special and ordinary, characterizes many astronomical phenomena. Solar eclipses are special when they occur in your location but happen somewhere on Earth every few years. Meteor showers are annual events but remain thrilling to observe. The full moon rises predictably each month, but still captivates those who pause to observe it. Similarly, a Betelgeuse supernova would be both a rare local event and a common cosmic occurrence, special to us while being ordinary to the universe. The philosophical implications of this duality relate to questions about meaning and significance. What makes something meaningful? Rarity, impact, personal experience. A Betelgeuse supernova would score highly on all these dimensions for human observers, but would mean nothing to the universe itself, which lacks consciousness or intention. Meaning, in this view, is something that conscious beings assign to events based on their understanding and experience, not a property inherent in the events themselves. Yet the assignment of meaning is not arbitrary or purely subjective. A supernova genuinely does represent stellar death and elemental creation, facts about physical reality rather than mere human interpretation. The explosion truly does feed the cosmic cycle of matter, contributing to future star and planet formation. These facts provide objective grounding for the meanings we construct, even though the process of meaning-making itself involves subjective and cultural elements. The intersection of objective reality and subjective experience defines the human relationship to the cosmos. We observe a universe that exists independent of our observation, yet our observations and understanding give us a relationship to that universe. We are both part of cosmic evolution, products of billions of years of physical and chemical processes, and observers of that evolution, capable of comprehending our own origins and context. This dual role, participant and observer, makes possible both scientific understanding and philosophical reflection. Betelgeuse, observed from our vantage point 650 light-years away, illuminates this dual role. The star evolved according to physical laws, fusing elements in its core, expanding into a red supergiant, losing mass through winds and ejections, all following deterministic processes. Yet our observation of Betelgeuse, our scientific investigation of its properties, our anticipation of its eventual explosion, these represent conscious engagement with cosmic processes. We are not passive receivers of sensory input, but active investigators, building theories, making predictions, and testing our understanding against observations. This active investigation has characterized human intellectual development throughout history. Ancient astronomers tracked planetary motions and predicted eclipses despite limited understanding of the underlying physics. Medieval Islamic astronomers preserved and extended Greek astronomical knowledge, making observations that improved accuracy. Renaissance astronomers including Copernicus, Tycho, Kepler, and Galileo revolutionized our understanding of the solar system's structure. Each generation built on previous work, gradually assembling a more accurate and comprehensive picture of cosmic reality. The process continues today as astronomers use tools and techniques that previous generations could not have imagined. Space telescopes observe in wavelengths blocked by Earth's atmosphere, revealing universe aspects invisible from the ground. Interferometry combines light from multiple telescopes to achieve resolution impossible with single instruments. Spectroscopy dissects starlight into components, revealing composition, temperature, velocity, and magnetic fields. computer modeling simulates stellar interiors and supernova explosions with increasing realism. Each advance brings new understanding and raises new questions. The questions surrounding Betelgeuse exemplify this ongoing process. We understand the basics of red supergiant evolution, but remain uncertain about details like mass loss rates, convection patterns, and internal rotation. We know supernova occur through core collapse, but still debate aspects of the explosion mechanism. We predict that Betelgeuse will explode within the next 100,000 years, but cannot narrow the time frame more precisely. Each observation refines our understanding while revealing gaps that require further investigation. This inherent uncertainty does not indicate failure, but rather reflects the nature of scientific knowledge, which remains always provisional and subject to revision based on new evidence. Science does not claim perfect or complete knowledge, but rather offers the best current understanding based on available evidence and theoretical framework. As evidence accumulates and theories improve, scientific understanding evolves, becoming more accurate and comprehensive even if never perfectly complete. The case of stellar evolution illustrates this progressive improvement in understanding. Early 20th century astronomers recognized that stars generated energy through some unknown process in their interiors. By the 1920s, Arthur Eddington proposed that nuclear fusion might power stars, though the specific reactions remained unknown. In 1938, Hans Bethe identified the proton-proton chain and CNO cycle as the main fusion pathways in stars, work that earned him the Nobel Prize. Subsequent decades brought increasingly detailed understanding of stellar structure, evolution, and nucleosynthesis. Today's stellar evolution models incorporate physics from quantum mechanics, nuclear physics, fluid dynamics, thermodynamics, and general relativity. They track changes in composition, temperature, pressure, and density throughout a star's interior as fusion proceeds. They model convection, radiation transport, mass loss, and rotation. They predict observable properties like luminosity, temperature, radius, and chemical abundances. While uncertainties remain, particularly regarding processes like convection and mass loss, modern models reproduce observed stellar properties with impressive accuracy. Applying these models to Betelgeuse requires determining the star's fundamental properties: mass, age, composition, and rotation rate. Each property carries uncertainty, and these uncertainties propagate through the models, affecting predictions about the star's current state and future evolution. Mass estimates for Betelgeuse range from about 15 to 20 solar masses, a 33% uncertainty that significantly affects predicted evolutionary timescales. Age estimates depend on mass and other assumptions, leading to uncertainties in how long the star will remain a red supergiant. Despite these uncertainties, we can make robust general predictions. Betelgeuse will eventually exhaust its nuclear fuel, build an iron core, and collapse to form either a neutron star or black hole. The collapse will trigger a core collapse supernova visible across interstellar distances. The explosion will eject several solar masses of processed material into the interstellar medium. These predictions follow from well-established physics and will occur regardless of the exact details of Betelgeuse's current properties. The timing remains the major uncertainty. Betelgeuse might explode tomorrow or tens of thousands of years from now. This range of possibilities stems from uncertainties in the star's current evolutionary state and in the physics of core burning in massive stars. The final stages of evolution, from silicon burning to iron core collapse, proceed so rapidly that small changes in initial conditions can affect timing significantly. A star that begins silicon burning might have weeks or months before collapse, too brief a time for us to observe precursor signals unless we happen to be watching when it started. Potential precursor signals to a supernova have been theorized but not definitively observed. The star might exhibit unusual variability as internal instabilities develop. Neutrino emission might increase as the core approaches collapse, though detecting this increase requires neutrino telescopes monitoring the star constantly. The star might brighten or dim significantly in the hours before explosion as internal conditions change. However, given Betelgeuse's known variability, distinguishing true precursors from normal fluctuations would be challenging. The best strategy remains constant vigilance. Automated telescopes monitor Betelgeuse's brightness regularly, looking for any significant changes. When changes occur, as during the Great Dimming, the astronomical community mobilizes to collect detailed observations. If Betelgeuse begins truly unusual behavior that might signal imminent collapse, rapid response observations would commence, attempting to capture as much data as possible before the explosion. Meanwhile, neutrino observatories maintain readiness to detect the neutrino burst that would precede the optical brightening by hours. This state of preparation reflects lessons learned from SN 1987A, the 1987 supernova in the Large Magellanic Cloud. That explosion provided the first opportunity to test supernova theory with modern instruments, and several neutrino detectors successfully captured neutrinos from the core collapse, confirming theoretical predictions. However, optical observations began only after the star had already brightened significantly, as no one was specifically monitoring the progenitor star when it exploded. For Betelgeuse, constant monitoring ensures that we will not miss the initial stages of the explosion. The international coordination required for this monitoring effort exemplifies modern astronomical practice. No single institution or nation controls astronomical research. Instead, astronomers worldwide collaborate, sharing data and coordinating observations. Telescopes in different hemispheres can maintain continuous coverage of targets. Space-based and ground-based facilities provide complementary capabilities. Professional and amateur observers contribute to comprehensive monitoring programs. This collaborative approach maximizes scientific return and ensures that important transient events get observed appropriately. Funding for these activities comes from government agencies, universities, and private sources across many countries. The scientific value justifies the investment, as astronomical research advances both fundamental understanding and practical applications. Technologies developed for astronomy, from charge-coupled devices to image processing algorithms to adaptive optics, find uses in medicine, defense, communications, and consumer electronics. Astronomy also provides educational benefits, inspiring students to pursue science and engineering careers and offering opportunities for public engagement with science. The economic return on investment in astronomy has been studied and generally found to be positive. Beyond direct technological spin-offs, astronomy contributes to scientific literacy, international cooperation, and cultural enrichment. These less tangible benefits are harder to quantify, but arguably more important than economic considerations. A society that supports astronomical research signals commitment to long-term thinking, fundamental understanding, and exploration beyond immediate practical needs. These reflections on the value of astronomical research connect back to Betelgeuse and its eventual supernova. The scientific knowledge gained from observing the explosion would justify decades of monitoring and preparation. The technological capabilities developed for studying supernova would find applications in other fields. The educational and cultural impact of witnessing a nearby supernova would inspire a generation of students and engage the public with science. The international cooperation required to observe the event would strengthen scientific collaboration across nations. Beyond these practical considerations, the supernova would serve a deeper purpose, expanding human knowledge and understanding of the universe we inhabit. This expansion has intrinsic value independent of practical applications. Understanding how stars evolve, how elements form, how energy and matter interact under extreme conditions, these insights enrich human consciousness and contribute to our collective intellectual heritage. Future generations will inherit this knowledge, building on it to reach deeper understanding. The story of Betelgeuse and Orion, from ancient myths to modern astrophysics, illustrates humanity's intellectual journey. We began by recognizing patterns in the night sky, telling stories to explain and remember those patterns. We developed mathematics to describe celestial motions quantitatively. We invented telescopes to see farther and more clearly. We discovered spectroscopy to analyze the light from distant objects. We developed nuclear physics to understand stellar energy generation. We built computers to model complex physical systems. Each step expanded our understanding, revealing new questions even as it answered old ones. This journey continues into the future. Next-generation telescopes will provide even more detailed observations of Betelgeuse and other red supergiants. Improved computer models will simulate stellar evolution with greater accuracy. New physics might emerge to explain observations that current theories cannot accommodate. Perhaps we will develop technologies that allow direct sampling of material from stellar winds, bringing actual stardust into terrestrial laboratories for analysis. Perhaps we will discover life elsewhere in the universe and learn whether other intelligences have studied the same stars we observe. These speculations remind us that science is an open-ended enterprise without predetermined conclusions. We investigate nature, discover its patterns, and build theories to explain those patterns. The theories work until they do not, at which point we revise them or replace them with better theories. This process has no foreseeable endpoint. There will always be deeper levels of understanding to pursue, new phenomena to investigate, and unexplained observations to puzzle over. Betelgeuse, in its twilight years as a red supergiant, stands as both an ending and a beginning. The star's life cycle approaches its spectacular conclusion, but that conclusion will seed new beginnings elsewhere in the galaxy. The heavy elements forged in Betelgeuse's core and created in the supernova explosion will disperse into space, eventually incorporating into new molecular clouds. These clouds will collapse to form new stars, some with planetary systems that might harbor life. The cosmic cycle continues, death feeding birth, destruction enabling creation. We observe this cycle from our unique vantage point as conscious, curious beings capable of understanding our own cosmic context. We know that we are made of elements created in stars, that we inhabit a planet formed from the debris of ancient supernova, that we orbit a star that will eventually die and return its material to the interstellar medium. This knowledge does not diminish us, but rather provides profound context for human existence. We are not separate from the cosmos, but deeply embedded in its evolutionary processes. Looking up at Orion on a clear winter night, we see this cosmic story illustrated in starlight. Betelgeuse glows with the deep red of a dying star, its enormous size and advanced evolutionary state obvious even to casual observation. The surrounding stars, younger and hotter, mark different points in stellar evolution. The Orion Nebula shows a stellar birth, while Betelgeuse approaches stellar death. Together, these objects tell the story of how stars live, evolve, and die, how elements form and disperse, how cosmic evolution proceeds over billions of years. The story continues, as it has for nearly 14 billion years since the Big Bang and will for trillions of years into the future. Betelgeuse will explode, enriching the interstellar medium and leaving behind a compact remnant. New stars will form, live their lives, and die in turn. Galaxies will evolve, colliding and merging, forming new structures. The universe will continue expanding, its ultimate fate depending on dark energy and other factors we do not yet fully understand. Through all these changes, physical laws remain constant, providing the framework within which cosmic evolution unfolds. Our brief moment of observation, a few thousand years of recorded astronomy within billions of years of cosmic history, gives us a window into these vast processes. We see stars as they were centuries or millennia ago, their light having traveled across interstellar distances to reach us. We study galaxies as they appeared billions of years in the past, looking back through time toward the cosmic beginning. We cannot see the future, but we can predict it based on physical understanding, calculating how stars and galaxies will evolve over coming eons. Betelgeuse's future explosion, whenever it occurs, will add one more data point to humanity's astronomical record, one more observation testing our theories against reality. The explosion will teach us about supernova physics, stellar evolution, nucleosynthesis, and compact object formation. It will provide educational opportunities and inspire wonder. It will change the night sky for our descendants, who will see a different Orion than the one we know. And it will continue the cosmic cycle of matter and energy that has operated since the first stars formed in the early universe. Until that moment arrives, Betelgeuse shines on, a magnificent red beacon in Orion's shoulder, visible to anyone who looks up on a winter evening. The star pulsates with its characteristic rhythm, its surface churning with giant convection cells, its stellar wind carrying mass into space, its core burning helium and building toward the iron collapse that will end its life. All of this happens according to physical laws we have decoded through centuries of observation and thought, yet the star itself remains indifferent to our understanding, following its evolutionary path regardless of human observation. This indifference does not make our understanding worthless, quite the contrary, it makes that understanding more remarkable. We have decoded nature's language, mathematics, and physics, and used it to comprehend processes occurring at scales from subatomic particles to galactic superclusters. We have built telescopes to see across billions of light years, instruments to detect individual neutrinos, and computers to simulate cosmic evolution. We have, in short, developed science, humanity's most successful tool for understanding reality. The study of Betelgeuse and Orion demonstrates this success, while reminding us of remaining mysteries. We understand stellar evolution in broad outline but debate details. We can predict that Betelgeuse will explode but not exactly when. We comprehend the physics of nuclear fusion but continue refining our models of stellar interiors. Science progresses through this combination of knowledge and uncertainty, solved problems and open questions, understanding and mystery. As we conclude this exploration of Orion and Betelgeuse, we return to where we began, looking up at the winter sky and recognizing the familiar pattern of the hunter. But now that pattern carries layers of meaning beyond simple recognition. We see Betelgeuse not just as a bright red star, but as an enormous red supergiant nearing the end of its life. We understand that the light reaching our eyes left the star centuries ago, that we observe the past rather than the present. We know that someday, perhaps tomorrow, perhaps millennia from now, Betelgeuse will explode in a catastrophic supernova, briefly outshining all other stars and leaving behind a neutron star or black hole. This knowledge transforms our experience of the night sky. Simple observation becomes cosmic contemplation as we recognize our connection to the stellar processes that created the elements in our bodies. Looking at Orion, we see not just a constellation but a laboratory of stellar evolution, where stars at different life stages coexist in the same region of sky. We witness ongoing star formation in the Orion Nebula and imminent stellar death in Betelgeuse. We observe the cosmic cycle that has operated throughout the universe's history and will continue far into the future. The hunter watches over the winter sky, his form outlined by stars that have guided travelers, marked seasons, and inspired wonder for millennia. This pattern will persist even after Betelgeuse explodes, though it will look different, missing its distinctive red shoulder star. Future generations will know Orion differently than we do, but they will still recognize the pattern, still tell stories about the hunter in the sky, still use these stars to navigate and mark time. And they will remember, if our records survive, that in the early 21st century, astronomers observed Betelgeuse undergoing a dramatic dimming episode, the great dimming that revealed the violent nature of red supergiant atmospheres. They will know that we monitored this star carefully, anticipating its eventual explosion and preparing to observe it with every available instrument. They will understand that we recognized Betelgeuse's significance both as a scientific object and as a cultural icon, a star that connects us to the cosmos through both knowledge and wonder. This dual connection, through understanding and appreciation, defines humanity's relationship to the universe. We are scientists studying physical reality and poets celebrating cosmic beauty. We are calculators of stellar masses and dreamers inspired by starlight. We are both, simultaneously, without contradiction. Betelgeuse speaks to both aspects of human nature, offering mysteries to solve and beauty to appreciate, knowledge to gain and wonder to experience. The story of Orion and Betelgeuse, from ancient mythology to modern astrophysics, from the Great Dimming to the anticipated supernova, encompasses thousands of years of human observation and thought. It illustrates our growing understanding of the cosmos, while reminding us of the vast scales of space, time, and energy involved in cosmic processes. It connects us to our origins in stellar nucleosynthesis, while pointing toward futures we can barely imagine. Most importantly, it demonstrates that the universe rewards curiosity and investigation with profound insights into the nature of reality. As we stand beneath the winter sky and trace Orion's familiar form, we participate in an activity that connects us to every human who has looked up and wondered about the lights above. We share their curiosity while possessing knowledge they could not have imagined. We see further, understand more deeply, and can predict with reasonable accuracy what will happen to these stars over cosmic timescales. Yet we also share their wonder, their appreciation for celestial beauty, their sense of connection to something larger than individual human concerns. Betelgeuse glows in Orion's shoulder, a red giant approaching its end, a fusion furnace burning through its last nuclear fuels, a star on the edge of catastrophic collapse. It shines across 650 light-years of space, its light a messenger from the medieval past, carrying information about conditions that existed when that light began its journey. We receive this light, analyze it with sophisticated instruments, interpret it through physical theory, and understand what it tells us about the star that emitted it. This is astronomy, receiving ancient light and reading in it the story of distant objects, decoding cosmic messages written in the language of physics. This is science, building theories from observations, testing predictions against reality, revising understanding based on evidence. This is human curiosity, wondering what lies beyond our immediate perception, investigating the unknown, seeking to understand our place in the cosmic order. Betelgeuse and Orion offer all of this and more. They provide scientific puzzles to solve, natural beauty to appreciate, cultural connections to past and future generations, and profound insights into cosmic evolution. They remind us that we inhabit a dynamic universe where nothing lasts forever, where creation and destruction intertwine, where endings feed new beginnings. They show us that we are part of this cosmos, products of its evolutionary processes, witnesses to its ongoing changes and students of its physical laws. The hunter watches, the red giant glows, the cosmic cycle continues, and we, for this brief moment in cosmic history, observe and understand, participants in and witnesses to the grand story of existence itself. The Great Dimming has passed, Betelgeuse has recovered, and the star continues its journey toward supernova. We watch, we wait, we wonder, and we prepare for the spectacular explosion that will someday, somehow, transform our view of Orion and add another chapter to humanity's understanding of the stars.